Hey everybody, welcome to this video on Newton's Law of Cooling. We're going to do these practice problems together. All right, so in our previous activity, we did our Desmos task where we were using transformations. We were transforming y equals e to the x, our exponential graph. And we realized we could use transformations to fit something. It was like a cup of coffee cooling down to the outside temperature, and we made a formula. And so here's a version of the formula we used through transformations. So we're going to apply this to some different types of scenarios. So first, let's recall how our Newton's Law of Cooling formula works. Okay, so we have capital T, or big T. Okay, this is going to be temperature. Temperature. Okay, big T stands for temperature. There's this subscript S, temperature sub S. This is going to be the temperature of the surroundings, the environment our drink is placed into, or we're going to do an example with an apple pie. Okay, and then there's the coefficient. It's right here, D sub 0. D naught is how we might say that. D naught. Okay, so what this number is, it's the coefficient on our exponential term. And D stands for difference, D for difference. And we're going to take, it says T sub 0 minus T sub S. This is saying the difference is the temperature of the object subtracted by the temperature of the surroundings. So maybe that clarifies a little bit those subscripts. And then this K right here, this is up in the exponent. This is it says it's constant. It's the rate of cooling is what it's called. It's going to tell us how fast or slow like the object would warm up or cool down to the temperature it's in. And there's a negative built into our exponent, so it's kind of hard to see, but don't forget that. Remember how when we did our transformations, we needed to reflect our graph across the y-axis, and by doing so, we make our exponent negative. And that way our object cooled down in temperature. Okay, so instead of having like X and Y, we're going to have a capital T and a lowercase t. So over here, we could do this a little more generally and just say, let's see, hold up. Y equals temperature of surroundings plus difference in temperature. You could just leave it as D times e to the negative k x. So the x and the y are like an ordered pair. But just to be more descriptive in our formula, we change these out for little t for time and big T for temperature. So function notation would just do T of t, but you could totally just do this. Temperature is equal to the temperature of surroundings plus the difference in temperature times e to the negative k times time. All right, so that's just breaking down the formula we went through with our Desmos activity. So let's apply it to a different scenario. As you're going to see, there's going to be two phases. So phase number 1, we need to solve for K. And K, what it's standing for is the rate of cooling. All right. The second phase is to actually answer the question. All right. Two phases. And it gets kind of tricky because there's all these numbers and where do we plug them in? So we're going to go over that. All right, here we go. Let's read our problem. An apple pie is taken out of the oven with an internal temperature of 325 degrees Fahrenheit. It's placed on a rack in a room with a temperature of 72 degrees Fahrenheit. So bake apple pie, take it out of the oven, set it on the kitchen counter. After 10 minutes, the temperature of the pie is 200, so the pie is starting to cool down. Here's our question, like the question we're going to answer. What will the temperature of the pie be 30 minutes after coming out of the oven? All right, we got to break this down. There's lots of numbers. So in our solve for K step, we need to know the temperature of the object, the temperature of the surroundings. We're going to use these to calculate the difference between those, D for difference, which is object first minus surroundings. Then we also need to know a time temperature. Let me write this out in words. A time temperature reading, basically an ordered pair on our graph. So we need a lowercase t for time that's paired with a temperature. So pretty much in phase 1, we don't use the info out of the question yet. Okay, we haven't made our formula to be able to answer the question. So that comes in our second phase. Alrighty. So let's see what we have. We're going to start with, and you know what? We're probably going to need more space to write this out. So I'm just going to move that up there temporarily. Okay, here we go. What do we know? We have the temperature of the object, the apple pie. All right, there it is. It's 325 degrees Fahrenheit, okay? And the temperature of the environment it's placed into, so like the room, is 72. All right, 72. Oops. So let's calculate the difference in the temperature. So we do object temp minus environment temp. Okay, so that's going to be 325 subtract 72. All right, 325 subtract 72, 253. All right, so D is 253. All right, cool. Let's keep reading. We have after 10 minutes, the temperature is 200. So these two pieces are paired together. Like you set a timer, 10 minutes, then you put a thermometer in the oven, in the apple pie, and you took its temperature. So these two numbers are paired together. We call that an ordered pair. And we have a time and a temperature. Okay, so our time temperature is like 10 minutes, 200 degrees Fahrenheit. So using all of this, we're going to plug in and get the first part of our model or our formula. All right, here we go. So the temperature of the surroundings. So that is 72. Okay, we've got 72 equals. Oh, hello, wrong spot. T for temperature equals 72 plus difference in temperature. Okay, difference in temperature, 253. 253 multiplied by E to the negative K. We don't know how fast this thing's cooling down, so K is unknown. And then little t. Okay, this is our beginning formula. There's one too many variables here. That K is what we have to solve for. So in order to solve, this is where we use our time temperature. And it's like an X or a Y, right? This is a time temperature. We're going to plug those in to big T, little t respectively, solve, and then we've got our K value. Okay, here's what this will look like. So we're going to do 200 equals 72 plus 253e to the negative k multiplied by 10. All right, we are going to solve for k. All right, so this is our solving logarithmic equations, or not logs, we'll use logs, solving our exponentials. All right, so go ahead and pause the video, see if you can do the steps to solve for k, and then check back in. All right, let's see how you did. So first off, we're going to subtract 72 to both sides. That's going to be 128 equals 253e to the negative k multiplied by 10. Next up, divide by 253. And then we're definitely just leaving this as a fraction. 128 over 253 equals e to the negative k multiplied by 10. All right, cool. We've got our exponential term by itself. This is when we apply the natural log function to cancel exponential function. So apply natural log to both sides. All right, we're going to have natural log of 128 over 253 equals negative k multiplied by 10. And right here, you guys, negative k multiplied by 10. You could rearrange this, and I'm going to. It's just negative 10 multiplied by k. So let's change that. Negative 10k. It's the same thing. Negative k times 10. So divide by negative 10, divide by negative 10. And then, oops, this is our k number that we're going to get an approximation for. So k is equal to this stuff, and then calculator time. So natural log of 128 over 253, close parenthesis, divide, negative 10. And let's pick up 4 decimal places. So 0.0681. K is equal to 0.0681. I better double check that. All right, cool. Okay, so that's kind of a long process. And guess what? We didn't even answer the question yet. Alrighty. So here's our K number. What we're going to do with this is plug it back into our model right up here for K. And now we have our completed formula. We know how fast the apple pie is cooling down, and therefore we can know what the temperature will be at different times. And we're out of space. I'm going to write this down here. Let's see. Okay, here we go. So here's our phase 2, where we actually answer the question. So let's remind ourselves of what our question was. Alrighty, what will the temperature of the pie be 30 minutes after coming out of the oven? So we need to solve for temperature, big T, and we know little t, 30 minutes. Alrighty. So here we go. Let's set up our completed model. So T for temperature is 72 plus 253e to the negative. Plug in K, 0.0681, little t multiplied by T. Okay, plug in 30 minutes. So what's the temperature? 72 plus 253e to the negative 0.0681 multiplied by 30. And then to solve for this one, our variable is already by itself, which is great. So we just need to put all this into the calculator. All right, let's do it. We've got 72 plus 253e multiplied by negative 0.0681 times by 30. All right, so 104.8 degrees Fahrenheit. 104.8 degrees Fahrenheit. Okay, guys, there you go. So it's a long process, but it's basically the same every time. So 2 phases. Let's recap what we did. Okay, we had to solve for K. That's like probably the hardest part. So we set up our model. We solved for K. Then we re-plugged in K and completed the model. Now with our model/formula, we can answer the question, which is where we plugged in the 30, calculator time, and cool, we've got it. All right, guys, you guys will try number 2, and I'll catch you in the next video.